Hey there, general physics students. This is Mr. Tro coming to you from his home. Here to do Module 1 with our first installment of the e-learning for this part of the unit. So I'm going to talk to you a little bit about the basic introduction to a circuit, what the vocabulary is within parts of a circuit, and talk to you a little bit about the different types of circuits that we're going to be learning about in physics. Okay. Just to let you know, this presentation is linked in on Schoology if you want to see the full presentation, which would have obviously links to the videos if you want to watch those. But there's also a PDF for you that you can download, and however you want to take notes. If you want to annotate them along with me on Schoology or on Notability and split screen your iPad, you can certainly do that. If you'd rather do it on with pen and paper, I get that too. So whatever floats your boat. So here we go. We're going to talk about the basically what is a circuit. You probably know this already, but a circuit, we call it, typically it's a closed loop in which electrons can flow. So you're familiar with circuits. Right now you're holding one probably in your hand, the iPad, or your phone, which undoubtedly is close to your body right now. It's just a series of different circuits, different microprocessors. And granted, they're not going to be similar. They're going to be much smaller than the circuits we would typically do in physics class or deal with in physics class. But nonetheless, they allow a closed loop for electrons to flow. Now, in chemistry, you learned about electrons. Electrons are the part of the atom. They're not the protons or the neutrons in the nucleus. They are the part you find outside we call them rings, or in the electron cloud. And since they're on the outside of the electron cloud, right, they're able to be lost very easily. They can be gained or they can be lost very easily. And because of that, if you have the situation correct, or if you have a situation where you can have an electrical reaction occur, like in a battery, or you have a power plant that can create electricity, free-flowing electrons, they can flow through wires, conductive wires, and as long as you close that circuit up, you can have what's called a conductive circuit. So you need a closed loop for those electrons to flow through. The parts of a circuit that we're typically going to see is a battery or voltage source. In physics class, we would deal with just a battery, but you obviously can plug into a wall. That's an actual voltage outlet that's connected to transformers and ultimately a power plant. So it's a little more complicated than a battery, but same sort of concept. You need wires. Those are flowing through walls right now. They're all throughout. They're in the resistors and the microprocessors that are in your devices you're holding. Resistors is a kind of a general term for anything that draws power. So an appliance like a toaster, a microwave, even the charger that you have plugged into the wall right now, that would be a resistor. Okay. Also, we can group in things like light bulbs. Are also types of resistors. So resistor is a very vague or general category. It pretty much covers anything in your daily life that would draw electrical power and use electrical power. Switches, you're maybe familiar with the term light switch. They basically turn a circuit on or off. So rather than having to like remove the battery or remove the power source or actually go in and disconnect a wire, it's nice to put a switch in line with one of the wires, and all you got to do is flip it temporarily, and it can temporarily break that loop. It can close that loop, or it can open that loop. So those are the basic terminology for what's in a circuit and what a circuit is. If we were in class, what I would give you is we would give you a battery. So if you just picture like a typical D-cell battery, right? That battery would have what's called the positive terminal and the negative terminal on it. If you ever put batteries in a device, you know what that means. We would give you a wire, right? So there you go, beautiful drawing of a wire. And then we would give you a light bulb. And the light bulb would have basically its base, and then it would basically go up into a bulb like this. And you would see inside the actual light bulb, forgive me, my drawing is amazing, I know. You'd have one lead going up from the side of the battery or the light bulb, and another lead going up from the bottom of the light bulb, and you'd have what's called a filament between those two leads. And if you can run electrical current, if electrical current can run right up one side and then back down the other, right, then you can have, as long as current can run across that filament and back out, so it goes in there and out the other way, you can light the light bulb up. So we would have given you these different items, and we would have asked you with your partners to see if you could create 4 different ways to light that light bulb up, given just the wire, just the bulb, and just the battery. Now, the battery gives you an electrical reaction inside that creates a potential difference. We'll talk about this later, but there'd be a potential difference between the positive end and the negative end. So if you could just connect a wire to one end and connect it to the other end, you're creating a closed loop for those electrons to flow. We learned in chemistry that electrons are negative, and so like charges, 2 negatives would repel each other. So electrons would literally leave the negative end and they would flow around into the positive end. This is very rudimentary. There's a lot more to it than that. But if you think about it, they would kind of flow through the circuit like this. So if we could put a wire there and somehow connect that, we could get a circuit going. And if we put a light bulb in the mix, those electrons would have to flow through the light bulb as well. Okay? So I'm going to just do the first one for you, show you one way, probably the first way that most people would get this to light up. And then if you want to pause the video and try on your own to figure out the other 3 ways, that would be something you could do. All right? So after a lot of trial and error, typically the first situation that most students would create is with their battery, right? They would have it like that. They would put the light bulb like that. My drawings are amazing, I know. They put their bulb like that, and they would take their wire, and they would connect their wire to one side, and the wire would come around, and they would connect it to the side of the bulb. And what would happen then is the electricity would flow down the wire. Forgive me, let me get a little thicker highlighter. It would flow down the wire. It would go through along this electrode there, go through the filament, and then exit down the bottom, and then get put back into the battery to go through the chemical reaction again. And you'd have a closed circuit there. Okay, so that's just one arrangement. Understand, right, that there needs to be a contact to the negative part of the battery, a contact to the positive part of the battery, right, and a contact to the bulb in 2 places as well. So why don't you pause the video at this point and see if you could create the other 4 types or arrangements for lighting that light bulb up. Okay, and then if you've tried, come on back and then you can see if you got it. Okay, so I'm assuming you've tried already. Hopefully you've realized that you could keep the battery in the same arrangement, but you could put the light bulb, you could put the bulb over here like that, and then you could connect your wire to the side like that. So it's pretty much the same arrangement. It's the same arrangement as the previous one, except you put the light bulb on the negative end of the battery instead of the positive end of the battery. And then hopefully, maybe you thought about the fact that since there's 2 contact points on the bulb that need to always be touching the 2 parts, the negative and positive ends of the battery, hopefully you realized that you could also just turn the bulb on its side. So if you put the side of the bulb, put the side of the bulb like that. That's a terrible light bulb, I'm sorry. If you did that, then you could run a wire from the negative end and touch it to the bottom of the bulb. It would also light it up. And you could do that exact same thing to the other end of the battery. Okay, so there's the positive end of the battery. If you put the bulb This one's a little harder to do. You'd have to kind of have the bulb like that. That's typically the last one people can get when they do it, but you can actually run it there. So if you see, it's really only two types of arrangements. Either the bulb is going to be, sticking out from the battery with the bottom of it touching, or the side of the bulb could be touching the battery. Okay? So, obviously that'd be a little more interesting, a lot more fun if we were in class. But unfortunately, COVID-19 is not allowing that to happen. So, moving on here, we're going to get into some vocab here. Pretty exciting stuff, I know. But there are three different types of terminology for a circuit that we want you to know and understand. They are voltage, current, and resistance. So we're just going to kind of explain those here. First of all, voltage. You think back to earlier in the year, we talked about you have kinetic energy and you have potential energy. Well, one of the types of potential energy we had was electrical potential energy, and that's found in batteries. So voltage is a ratio of electrical potential energy. And if you know what potential energy is, you remember what potential energy is. It's literally stored energy, energy that's not yet being used. So a battery is a perfect case of this, right? The battery can sit for months, even years, and unless you actually connect it, the reaction inside is not really occurring, and therefore the energy is just kind of stored inside that battery. So it's electrical potential energy per charge. If you remember back to last unit, we had joules, right? Joules was our unit for energy, and there's a new unit now for charge. Had we done electrostatics, which is what we were going to do before the e-learning was enacted, we would have learned about this thing called a coulomb, which is the SI, it's the standard unit for charge in physics. But basically voltage is known as a joule per coulomb, and we have a special unit for that. We call it the volt. And you are used to volts, you know what volts are. You've heard of volts. You may not know this, but out of the standard wall socket, you usually have about 110 to 120 volts of voltage, of electrical potential. Most batteries, right, a standard battery gives out maybe 1.5 volts, like a AA or a AAA. Your car battery usually runs on about 12 volts. So there's a big difference in voltage, in potential energy, coming out of a wall versus a battery. But we call it electrical potential. It's the potential for electrical energy to be transferred from one device to another. So we'll oftentimes talk about it as potential difference. So we get used to that. What happens, though, is when you have an electrical potential, if one end of the battery has a different electrical potential than the other end of the battery, that causes electrons to move. The only way an electron is going to move is if it's forced to move. And so if an electron sees a different potential energy at one end, it'll start to move. Think of it as, and this is going to be a terrible drawing, but think of it as if you had a lake, right? If you had a lake and that lake was filled with water, it's not going to flow. But if I were to give that lake, if I were to give the one end of the lake and another end of the lake different potential energies, think back to last unit, we talked about gravitational potential energy. Now what's going to happen is that water will flow because it has a potential to do so. So that's what a kind of a battery does, is it just gives one end of the battery, one end of the voltage source has a different potential energy than the other, and electrons can flow. And when that battery gets used up, when it runs out of juice, basically, when the electrical or when the chemical reaction inside no longer can go, it's pretty much run its course, we say that the battery is dead. Well, what that means is there's no potential energy anymore from one end to the other. There's no way to make that potential, and therefore there's no current. Okay, so if there's no difference, then there's no current. Okay. There's a video here. It's pretty neat, actually. It's about high voltage wire workers. So this is linked in Schoology. It's on YouTube. I suggest you watch it. It's actually pretty awesome. But it all talks about potential difference and how they can work on the wires because of the way that they actually get rid of the potential difference before they get on the wires. Another reason why something similar is you look up all the time and you know that you're not supposed to touch electrical wires because you can get fried, you can get electrocuted. And that's true. But birds do it all the time, right? Birds sit on wires all the time. And this is going to be a wonderful drawing. You're going to love this. But basically, if you have a wire, right, and then you bring your old bird in. Here's my bird. Oh my goodness, look at that. That's a great bird. He's got wings. And we'll just give him a human head, okay? So when a bird's sitting on a wire, you've got a ton of electrical current that's flowing through that wire. Tons of current flowing through that wire. Enough to obviously kill you very easily. So what happens, right, is there is a term we haven't talked about yet, but there is such a high resistance. There's such a high resistance within the feet, if you will, of the bird or the animal, the squirrel, whatever's on the wire. There's such a high resistance there that the current is not going to want to leave the wire and go up and down through the bird. It's not going to do that because electricity, like many things, like think of it as flowing water, it's always going to go the path of least resistance. So it's going to come here and it's going to look at that and go, nope, it's just going to keep going through the wire because the wire offers it the path of least resistance. And so because both feet are basically at the same potential difference, according to the wire's vantage point, the electricity just kind of flows through the wire and stays in the wire. It doesn't actually go through the bird. Okay, so it's just kind of a practical application of that. All right. So that was potential difference. That was voltage. All right. Current. Think of current as the flow, right? Current is AKA flow of electrons. And you can think of electricity like water, flow of water. Obviously, the bigger pipe you have, the more flow you're going to have, the more current you're going to have. And if you were to back it up and you create more pressure, that would be resistance to that current. But it's basically the flow. When there's a potential difference in voltage, it creates a flow of electrons, and that is called current. Now we have a unit for current. It's called the amp. Technically, it's the ampere, but we call it the amp. We also, if you think about musical instruments, you think about connect your guitar to that amp. Well, an amp is just amplifying, right, the sound. It's a different kind of amp, but this kind of ampere is basically how much flow of electricity there is. All right. Now, in the equation you're going to learn later on with another teacher, in Ohm's law equation, the symbol for the amp is an I. If you remember back to previously, the symbol for voltage was a V. That made total sense. But we have to remember that not everyone that creates these symbols or finds these discoveries or works in the scientific community, not everyone is American. Not everyone speaks English. So the symbol for current is I because it's from a French term from intensity. It's intensity of flow. So it comes from a French term for intensity. That's why it's an I. All right? But it's how much charge can flow in a given amount of time. So it's basically the rate of flow. Like you have distance, and then the rate at which your distance changes is called velocity or speed. Same thing here. So this is like the velocity to distance. It's the rate at which voltage can flow. Okay? You might be familiar with a little band called AC/DC with that lightning bolt in it. That's no mistake, right? AC/DC refers to the two types of current that you can have. It can be either direct or it can be alternating. In physics class, we talk about direct current. Okay, we talk about direct current. Direct current is the type of current you get from a battery source. It's one-dimensional. It's one way, and it basically just flows from one end of that source to another, and it's quite useful. Many devices use direct current. Okay, actually, most of them do. If you've ever plugged something into the wall and it has one of those little bricks in the line of the wire, right, that's a converter. Basically converting the current out of the wall, which we call alternating current, into a form that your device can use which is direct current. So direct current is probably the most common type of current we would use in an appliance. But the reason we have alternating current, you might be asking, well, why do we use alternating current? And this is a much longer discussion, but the current that comes out of like a power plant, a power station, is alternating current. The reason being, it's a long discussion, but when you have a power plant, you basically generate electricity using turbines, and the turbines, the way the design of a turbine creates current, oscillating magnetic fields, which creates oscillating electric fields, which gives you alternating current, meaning that the charges move back and forth. And the reason we do that is because this can travel miles through wires, miles before it loses much energy. Whereas direct current will not travel very far through a wire. So you typically change it from alternating to direct current right at the source of your appliance or whatever you're using. Okay, but in physics class, we will just focus on direct current because we would use batteries. Okay, here's another video. Kind of recaps everything I've talked about so far, so I suggest you watch that. And the last term is resistance. Okay, so resistance is a measure of blank that current encounters as it passes through a material. Now, if you think about the word resistance, to resist something would be to kind of hold it up or to oppose it. So resistance is literally, it's a measure of the opposition. Okay. You are familiar with this term. I know you are. Think about passing periods at school, right? If you're walking to the bathroom during class, you might see 3, 4, 5 other people. Your flow to the bathroom, your trip to the bathroom is very easy, very simple. If you're trying to go to the bathroom during passing period, you've got hundreds of students everywhere, people crossing your path, people in your way, people walking in front of you, going slower than you. And so there's opposition. There's people in your way. You're trying to flow through that hallway, and there are things that are resisting you. So in any sort of circuit, there are going to be resistors, okay? And so resistance is literally the opposition that current encounters as it passes through material, okay? Its symbol is R, that makes sense. And its unit is something called the ohm. Okay, and that'll become a little more clear when another teacher teaches you about Ohm's law, where you use V and I and R. But the ohm is the unit for resistance. It's basically, you can think of it like a horseshoe. Okay, it's the omega symbol in the Greek alphabet. Okay, now it's kind of counterintuitive, but if you had a big, thick, like a wide hallway, it would obviously be easier to move through that hallway, right? So if you had a wide hallway, that hallway would have less resistance, okay? And we think of a wide hallway would be like a good conductor. It would be the best type of conductor. Think of like a highway that has 8 lanes of traffic versus 1 lane of traffic. Obviously, that highway is a better conductive material for those cars, right? So resistance is going to be lower in good conductors, and it's going to be higher in poor conductors. Good conductors, obviously, like copper. Copper is a good conductor. Most wires are made of copper. A poor conductor would be something like plastic or rubber, which is why people use rubber gloves and tools have rubber handles on them if you're going to work with electricity, because they're a very poor conductor. Therefore, they're highly resistant. Okay, and they can help you. They can keep you safe. So when you're talking about resistance, it's not just the material that can cause resistance. It's basically the length or the width of that material as well, or the temperature of that material. So there are 4 things that can affect the resistance that a substance has. Okay, if you think about it, yes, obviously, if you have a wire, if it's shorter, there's going to be less resistance because there's less path to travel. Okay, so that's pretty self-explanatory. I don't think we have to spend a whole lot of time on that. But shorter length has less resistance, sure. Okay, cross-sectional area or the width of the wire, if you think about it, right, if I had a big, thick wire, right, versus a thin wire, if you think about electrons flowing through that wire, right, you can get a ton of different electrons flowing through a thick wire where you can only get a few electrons flowing through a thin wire. So The more you can fit, the wider the hallway, obviously the less resistance there would be. Okay, so the greater the area, the less resistance. We talked about this already, but material, absolutely material, right? Metals tend to be, right? Metals are better resistors, or sorry, better conductors. So we can choose to make materials out of different metals. Copper's not the best conductor out there. Gold is a very, very good conductor, and silver is actually a very good conductor. Gold and silver are both much more conductive than copper, but they're far more expensive. In fact, if you think back to chemistry, right? If you think about gold, silver, and copper, they're all in the precious metals family of the periodic table. Well, they all have similar properties, right? So gold, if you ever were to buy like a speaker wire or something, or a HDMI cable from Best Buy or something like that, if they're gold plated, they typically get a little better signal. But gold and silver are way too expensive, way too expensive to be practical. So we typically use copper, okay? Aluminum is used a lot too. But we don't make wires out of plastic because plastic is a terrible conductor. And then temperature, lower temperature means less resistance. If you think about, and this is going to be tough for me to draw, but if you think about that wire, right, there are metal atoms, right, in that wire. They're lined up in a matrix, if you will. There are these metal atoms inside that wire, okay? Now we know these metal nuclei are sitting there, they have electrons free-flowing. Those atoms, if they're at normal, just normal room temperature, right, they're constantly vibrating. Those atoms are constantly vibrating. So if this sort of thing is happening, right, it's pretty easy for electrons to flow through between those. So think about, I don't know, these 10 people being in the middle of the hallway, right? You're trying to go a passing period. They're in the middle of the hallway, and they're just kind of rocking back and forth. You could get through them pretty easily, right? But if they were moving a lot more, it'd be a lot harder to get through that hallway, right? So if you think about it, if we have a low temperature, they're just kind of vibrating. You heat that wire up more, those atoms are moving a lot more. You heat it up a bunch, those atoms are moving a lot more. They're vibrating very quickly in place, and that creates a lot of disturbance. It creates a lot of resistance to the flow. So a hot wire is much more resistant than a cold wire. Okay, hopefully that makes sense to you. And then there is a Schoolhouse Rocks video here that you can watch. Brings me back. The last thing here before I take a break from these notes is you're going to be doing labs, Ohm's Law Lab and Ohm Suite Ohm labs digitally. You'll be doing them virtually. And they're going to use resistors. Now, if we were in class together physically, we would be using, instead of hooking a toaster up or hooking a TV up or your cell phone charger up to a circuit, we would be using these things called resistors. And so, these are manufactured in bulk, and they're sent out to kind of, they symbolize, or they kind of parallel what it would be like if you were to hook up a device into a circuit. If you notice, they have wires on one end, right? And then they have this body that creates resistance. So inside that, we don't need to talk about it, but inside that, basically the wire takes a lot of twists and turns and creates a certain amount of resistance for the electricity to flow through. Now, if you're looking at these, you notice that there are different colored bands on these resistors. So I just want to go through quickly how you would read those resistors, because they don't actually write the number. They don't write the ohms, the amount of ohms. They don't write that on the resistor itself. They print basically different colored bands, which is really nice for someone like me who's colorblind. But I've already figured out what the colors are here, so I can hopefully not lead you astray. But basically, every resistor is going to have one colored band that's kind of on its own, and it's going to be usually gold or silver. And that band, if you put that on the right, this is the we call it the tolerance. Right, if you put that on the right, then you're going to see that you're going to read 2, 3, sometimes even 4 different colored bands across the top. right? And each color has a digit associated with it. Okay, each color has a digit associated with it. The last one, the last band, colored band, is always going to be the multiplier. So it's going to tell you what to multiply the first 2 or 3 digits by. Right? So I know it's kind of confusing, but if you look, right, our first color is this guy, right? I believe. Yep. It's this guy, right? So that green indicates a 5. Our second color is that blue, which indicates a 6. So right now we have 56. And if that was all that was there, right, you'd have a 56 ohm resistor. Now the multiplier is either going to be, okay, it's either going to be it's going to be the last colored line before the tolerance. So if you look at the multiplier here, it's red, right? And that red indicates that our multiplier is 100. So we're going to basically multiply that by 100, which gives you 5,600 ohms. Okay? Or you can think of it as add however many zeros are in that multiplier, add that to the resistor. Okay? So this resistor would be 5,600 or 5,600 ohms. That's what that's saying. Okay? If you look at the bottom one has 4, right? It has 4 different colored bands, and then it has its tolerance. So it's got the 4, it's got the 7, it's got the 0. So that's 470. That's 470. And then it's got the multiplier as well, that is the red, which says 100. So that means you're adding 2 more zeros to it. So this would be 47,000 ohms of resistance. Okay. So, just to recap what that was, right, is the first value, the first color is the first value, the second color is the second value. There may or may not be a third band. If there is, that's great. It's another number. Then you're going to have the very last thing. So, for example, this would be my third. The fourth one, or the one that's right before the space that happens before you get to the tolerance, that's going to be your multiplier. So if we're looking at this guy, right, we're given the orange, which is a 3. We're given another orange, which is a 3, so that's 33. And we're given a white, which is a 9. Okay, so that's 339. That's what we have right now, 339. Okay, and then our multiplier, in this case, it's black. And if you look here, the multiplier for black is just 1. It just means you got to multiply it by 1, right? So I just multiply it by 1, and I end up getting, right? I end up getting my total resistance as just 339. So in class, you would be given a cup that has these different resistors in it, and you'd be expected to lay them out and then determine what the resistance are. Now I want to point out that you also have one more band here. The last band, right? That last band is going to tell you the percent error. Okay, so understand that these resistors are being pumped out thousands at a time in a factory, and you could spend more or less money for them. But typically, what you're going to see for that last band is you're going to see either a gold band or a silver band. So when you think about error, percent error, this would be a 5% error. This would be a 10% error. Now, when you go on and you go into the working world, in terms of making errors, you can make errors, right? People make errors all the time. Your boss will have a certain amount of tolerance for you making those errors. And so we call this tolerance. How much we're willing to give up, or how much we're willing to deal with, how much error we're willing to deal with. So let's just say, for example, we had a silver band, right? A silver band, or this one's a gold band, right? This is a gold band. So what that means is this resistor is going to provide you with 339 ohms of resistance, but it's not going to be perfect. It could be 340, it could be 337. Basically, you'd have to figure out what 5% of 339 is. Well, I know 10% is 33.9. So let's call that 34, right? So if it was 10%, right? If it was 10%, it'd be roughly 34 ohms. If it was 5%, that means it'd be about 17 ohms of error. So basically, I know that when I'm using this resistor, the company's telling me it's going to give you about 339 ohms of resistance, but it could be 17 up or down from that. So it could be 322 ohms all the way to 356 ohms, right? So this could be 322 all the way to 356 ohms. That's what that means, okay? I wouldn't spend a whole lot of time worrying about this. This would be a bigger concept if we were actually in class and we were doing these labs in person. You're going to most likely be doing these labs digital on a digital platform using what's called the Phys app, a simulation, and it's going to tell you what the resistors are. There's not going to be error involved in them, okay? But that is how those work, okay? This would be a great place for you to stop and pause the video. I'm going to keep going though because there's one more topic in the video. But just to recap, right, we have talked about the three different pieces of terminology that are super important to know about circuits: voltage, which is that potential difference in electrical energy; current, which is the flow; and resistance, which is how much opposition your circuit gives the flow of electrons. Okay. The last thing I wanted to talk to you about in this module 1 is the idea that we're going to be seeing throughout this whole unit, you're going to be seeing different drawings of circuits, and you're going to be expected to draw those circuits and know what those drawings mean. So it is not a very helpful thing for someone who is, for example, an electrical engineer or someone who is going to be putting the electricity into a building, for example. Say if you're building Buffalo Grove High School, they don't want to see drawings like this. They don't want to see that. They want a very detailed but very basic and kind of universal way of drawing circuits, and so we call those schematics. Blueprints, you might have heard of blueprints. Blueprints utilize these schematics. Okay, so basically what a schematic drawing is, or schematic diagram, is it uses symbols to show the different electrical components. So, excuse me, I'm going to take a drink here. So we have symbols for a battery, resistor, a light, and a switch, which there's way more than those, but those are the ones I want you to be familiar with. So I'm just going to go through those and kind of show you how they would be drawn, or different optional ways of drawing them. So typically when you're drawing a battery, you have the positive and negative ends. The longer line represents a positive terminal of a battery, and the shorter line represents the negative end. So basically the battery part would be this section right here. That indicates a battery. This is just showing wires, right? So these are wires in and wires out of the battery. Okay. So if you're going to draw a battery, right, you can just draw a line with a long line and then a short line and carry on. Okay, and that would be good. What you will see oftentimes, especially on homeworks, if we use an online resource to draw different schematics, you will also see this sort of deal to indicate a voltage source. This is typically used for like an outlet or like a power source that's not a battery. This is usually used to show a dry cell or a battery, whereas this is used to show like an outlet and a wall. Either way, they both mean a voltage source. They both have a positive, negative end. There might be times when we take multiple batteries, and you have this in your devices, right? You line up, two AA batteries in a row, end to end, negative to positive, negative to positive. If we're going to do that, we just simply take and we draw one dry cell followed by another dry cell back to back, right? And it would show both our batteries, right? Both our batteries back to back. So that's what that is. So if you're going to draw a voltage source in a schematic, it would look like one of these. Okay. The other parts of the schematic diagram look like this. You have a light bulb. Okay. This is technically what the symbol looks like. I personally find it easier to just kind of do a loop-de-loop like that through a wire. If you notice, if I turn that over, it's pretty much the same thing, right, as what's drawn there. But if you draw a loop-de-loop and then you just kind of put a circle around it, it's a lot easier to draw it that way. Obviously, if you're artistic and you don't want to do that, that's fine, but I just do that sort of thing, and I call that a light bulb. Okay, so that would work. Resistors, remember this could be any appliance. We call it the Charlie Brown. If you picture Charlie Brown's shirt, right? There's his, that's terrible. There's his shirt, yay, Charlie Brown. There's his arms, right? It's what he kind of has on a sweater that he wears all the time. But basically, it's showing that the current has to change direction. And anytime you change direction, think about if you're running and you have to change direction a bunch, that basically slows you down. So resistors slow down the current. They provide opposition to the current. So basically a resistor is going to be just a squiggly line like that, or a zigzag line. Switches, you have two types of switches, right? You have an open and a closed. With a closed, it's just simple, just draw a line and put two little dots on it to show that it's closed. If it's open, you're basically going to have a switch like that, right? That can be moved to be closed if you want it to be closed. Okay, but you have open and you have closed. When it's open, there's no flow, and when it's closed, the current does flow. Okay, wires are very simple. Wires are just lines. They don't curve though. Don't make them curved, right? They're going to be straight lines. Okay. So with that, there are two ways in which you can wire something. Now, the most basic circuit can be wired in series. If you think about series, you think about, I don't know, books. Think about the Harry Potter books, right? There are a number of books. They're one after the other. They're intended to be read in order. TV shows, right? You have seasons, you have episodes. Those you can think of as a series. They're intended to be watched in a particular order, and so a circuit wired in series means there's really only one way to do it. There's only one way to watch that show, it's to watch it in order. There's only one way to read those books, and that's to read them in order. There's only one way for current to flow through a series circuit, and that is from start to finish. It's going to, literally the current, if they're connected one after the other, the current only has one pathway, and that's very important. Only has one pathway through which to flow. So if we think about Mr. Electron here, Mr. Electron is leaving the battery source right there, right? He's leaving the source, okay? He goes down this wire here. Notice the wires are at right angles. He goes down that wire. He gets to this resistor. He has to give potential energy to that resistor. So this could be a light bulb. He could be lighting up that light bulb. And then whatever voltage is not lost to that resistor carries on, and what's left has to go through the other resistor, and then it goes back to the battery terminal, and then that completes the circuit. And then a reaction continues to go. So what you end up having, right, is you end up having tons of these different electrons flowing out all the time, right? And these electrons, they flow through the wire, right, and they flow all the way through. Some are deposited as they go through and used up, but basically you have one pathway. There's no other way for that electricity to flow. It has to flow through every resistor, okay, has to go through each one, okay? That's a series. Now the problem with series, if you were to, for example, break the wire right there, guess what happens? Yeah, you might have, hopefully you said it. If you break the wire, right, that whole circuit stops. There's no longer a closed loop for it to work. Or this happens all the time. Happened all the time in old Christmas lights, holiday lights, right? If one of the bulbs went out completely and busted, the entire strand of lights went out. Okay, that's not the best way to wire those things. And in fact, if you think about it, this is not the best way to wire your house either. Can you imagine if one light bulb burned out in a circuit in your house. So like, say like you got the family room, and that family room has 5 different outlets and 27 things that are plugged in. If one part of that circuit burned out, if it was wired in series, the entire room would not function anymore until you fix that one item. Okay, so we don't actually wire things in series very often. We wire them in parallel. Okay, parallel is just what it sounds like. If something's in parallel, it means it's got 2 or more different runs, basically. So what we do instead of just giving it one pathway to flow, we give the current multiple pathways to flow. So let's just picture that you are an electron, and you are leaving the battery here. You're going along, you're going along. You get to what's called a junction point. Okay, this is called a junction point. Excuse me. We call this a junction point. When you get to that point, as the electron, you have a choice. You can go left, or you can go right, door 1 or door 2, right? So you have resistor 1 and you have resistor 2. As an electron, you have a choice. Okay. Now, it's not that simple. Electrons are not people. They're not personified. They don't make choices like that. They're basically going to go where the resistance tells them to go, and you'll learn about that later in the unit. But as this electron, I can go through resistor 1, right? Dish off my energy to resistor 1 and come back. And I'm not going to go back through resistor 2 because the path of least resistance would be to go back to the battery at that point, right? So an electron can flow there, right? But if this electron chooses to go there, another electron coming through, right? He can choose to go this way, right? And then he can meet back up at the junction point and go back to the battery. So understand that there are 2 types of flow, right? There is the main flow, and then when you get to that junction point, right? When you get to that junction point, you have the option of going through resistor 1. You have the option of going through resistor 2. Either way you go, though, you're going to meet back up at some point and complete the circuit. Okay? Now, the beauty of this is, think about if resistor 1 were to break, right? Think of you're the red highlight, you're the red electron. You try to get here to resistor 1, okay? And you get there, but that resistor is broken, okay? So let's just say that resistor is broken. Let's just go here. It's broken like that, okay? You get here, you're like, uh-oh, I can't cross that bridge. You can go back, and you can still go through resistor 2, and you can still complete your journey, even if one is burned out, even if one is broken, okay? So that's the beauty of a parallel circuit, is in a parallel circuit, you have multiple pathways, okay? Multiple pathways for current to flow, and it allows you options. So this is how houses are wired. This is how all circuits in houses are wired. So if one thing burns out or one thing breaks, the rest of the house will still work. Okay. Now you're going to do labs later on in this unit, virtual labs, where you have to build circuits that are either in parallel or series. Okay, either in parallel or series, and hopefully this little tutorial has helped you. Okay, so that's it for Module 1. Just to recap, right, we have talked about basically what a circuit is. We've talked about the important terminology, voltage, and how voltage is potential. We talked about current and how that's flow of electricity or flow of electrons. We talked about resistance, which is the opposition to the flow, how they all go together. In the next module, I believe Mrs. O'Neill is going to lead you through Ohm's law, which mathematically relates voltage, current, and resistance together. We've also talked about things that affect resistance, how resistive a material is. We did a crash course here on how to read the resistor codes. There's lots of videos online for this as well, if you need help with that. And then we basically learned a little bit about the schematic symbols that can be used, and you're going to see for the remainder of the year. And then we talked about the 2 types of circuits, being series and being parallel. Okay. Hopefully that makes sense. Hopefully I didn't bore you too much. I know I was pretty excited doing it. So that ends Module 1. Again, please check out the videos that are posted. in the Google presentation, the Google Slides presentation. That link is on Schoology. And then it would be a great idea for you, while listening to this, to either annotate your notes on PDF or to write the important things down on paper and study it just the same way you would do in a regular class. Okay? So, once again, this is Mr. Tro signing off. I hope you enjoyed it.